So we want to talk about floating gate operation. In fact, we want to talk about floating gate operation that can occur at room temperature on a nice sunny day, or could actually happen all the way down to 4 degrees Kelvin, where almost everything turns into ice cubes, including liquid nitrogen, liquid helium, and water, and so forth. And what we want to be able to show is we get floating gate operation throughout the whole thing with sort of nominal retention. We get normal floating gate transistor operation, and we can program in arrays. This is going to be kind of a neat thing to show that we can get that entire range. Now, someone might ask, well, why on earth would you do floating gate for cryo? Well, thank you for the question. Because if you look at it, you might want it for satellites, you might want it for medical applications that operate at a whole range of different temperature levels. You might want it for all sorts of physics experiments, particularly, say, particles and so forth. As well as it's a very big deal for quantum computing, where part of it actually needs to be sitting at 4 degrees Kelvin or even smaller. And this could be an opportunity for doing interfacing at these spaces. Okay, so that works. We actually have a reason why. But somebody might say, yeah, but what about freeze out? Transistors won't work at 4 degrees Kelvin. Well, the physics are actually a bit more complex than that. If you look at a typical MOSFET, what you notice is that, of course, you're going to have your P regions and P-type material where the quasi-Fermi level will be sitting near the valence band, N-type material where the quasi-Fermi level will be towards the conduction band, and you'll maybe have degenerate P-type material, which is actually going to be inside of the valence band. And you think, okay, nice physics. But what you actually see is if you look at the quasi-Fermi level, that's where you can have a Fermi-Dirac distribution of carriers right at the Fermi levels where it's a half. So at room temperature, I'm going to still get a sizable amount of carriers sitting at the conduction band, and those are the ones that are often involved in conduction when we end up saying it's an N-type piece of material or P-type piece of material. So there are carriers, that works great. But at 4 degrees Kelvin, this goes like nearly flat, and you find out, well, there's almost no carriers in there, and it's nearly intrinsic material. You think that's not going to work unless the quasi-Fermi level happens to be actually in the valence band or conduction band already, in which case then you actually have carriers. So you actually have carriers in the P plus and N plus regions, but not in the N and the P regions. Okay. That changes the way the band structure looks like for a MOSFET operating sort of, say, at intrinsic levels. You'll see that in these cases that the depletion level is typically on the N side, but in this case it's going to be predominantly on the P side because the other part's going to look pretty much intrinsic. And so as a result, you will get that there are additional physics in terms of asking what is the capacitive divider in surface potential. All of this works, but probably a longer conversation. So you think, great, this would be great. And so this all started by a conversation, starting with David Riley saying, hey, wouldn't it be great to kind of do some of these measurements? Because you'd like to try like FPAs at cryo temperatures, and we'll need to do floating gates there, and they can be really useful for quantum computing. That's great. Of course, it also occurred to me to remember that, hey, we'd had some chips built once, thinking like, what Brian Degnan's put together in terms of a characterization chip, and kind of we're working through it, and so many long hours. But then, it turns out this eventually became useful, and you can see this is part of wafers that were then part of a chip. So we kind of get to the end of this conversation and go, wow, okay, let's actually go on a journey and go on an airplane, and we take a bit of time. 20 hours to sleep, 20 hours on a plane, get some sleep. And after all that, get to go visit this wonderful operation at University of Sydney that's connected with Microsoft, where there's this incredible amount of quantum computing kinds of structures that are being done. And so being there, we ended up taking this wonderful characterization chip and then decide to actually mount it on a board. And that board can then be put into liquid nitrogen temperatures. And there are many different tests of this, but we're going to kind of focus on this one test of these test structures where we look at the floating gate elements, actually looking at the sort of core structure that allows us to look at floating gate behavior and actually show it at 300 degrees Kelvin and at 4 degrees Kelvin, which really opens up the opportunity for non-volatile memories and other sort of mixed signal programmability, as well as things that might be important for connecting or computing or regressing values that come out of quantum computing applications. So this becomes the structure that we're looking at. And it's basically a typical sort of floating gate structure with where you have various capacitors, including capacitors to do tunneling. You have transistor. You also have a simple amplifier in the structure that can be used in different cases. And we use the floating gate structure with the amplifier for the floating gate measurement and for the tunneling, and you'll see that used. We also use a structure where we turned off the amplifier for the floating gate injection. You might ask, why two different modes? Because it shouldn't be necessary. Well, one little issue with the chip that is used is that this is a PFET for this transistor M1, and that PFET tends to inject. And so we get injection from the device we're characterizing and from that element. Now it can be used, and there's some wonderful possibilities out of it, but that's a bit more advanced than this conversation. So basically we can say the measurements work at 300K and 4K, and you might go, well, okay, where's my data? Well, here's some data, and you can kind of see from the data that in fact we did get tunneling and injection and sort of pretty good hold time in all of these. You're probably thinking, can somebody give me some more data? A little bit more explanation. Well, why, of course. So the first thing is that the amplifiers here are used for basic floating gate voltage measurements. So basically where you're going to end up sweeping the input, where it crosses over, you will actually get the floating gate voltage. And so you can actually see that we actually sweep the reference voltage in these cases. And so you can see it swept at 300K. You can also see it swept at 4K. One of the first things you notice is that this means the amplifiers definitely worked at the entire temperature range. And you can see that things actually moved. But let's actually go through that a little more carefully, because we can see that we actually have this core characterization structure, but in between, we do a tunneling step and an injection step. So let's walk through this a little bit. First, when we do a first measure, we do a first ramp through it, and we can actually see that things went from 0 to our 5-volt power supply that we use for all these experiments with these 350 nanometer ICs. Then we did a tunneling measurement. And we'll talk more about tunneling and the details a little later. We do a tunneling measurement. After we do that, then we measure again. And you notice that everything moves. And they move by different amounts, but they both moved at a fairly reasonable level and turns out to be predictable level. Then we do an injection measurement, again, not using the amplifier in this case, and then measure again, and we notice that we can put it right back to where we were before. So this is a classic sort of things you would expect for floating gates, and to say the floating gates work in a process. So this measurement shows, yes, it does work. But let's go a little further into the details. Let's start with electron tunneling. And what you see is we work through this integrating structure where the current that comes through that tunneling capacitor, the C-ton and V-ton, is then going to get integrated through the capacitor around the amplifier. And so we can then talk about it at 300K, and there's a decreasing voltage with time to show the tunneling, and measuring the slope actually gives us a measure of the current. And we can do the same thing at 4K, and these are both data from those cases. So from that, you can look at a whole range of things, but the beautiful part of the experiment is the voltage across the tunneling junction is fixed because the amplifier basically fixes the voltage at VREF through the whole thing. So this is a way to measure very tiny currents without ever needing to have sophisticated external equipment to make this work. And as a result, you get two really interesting slopes on this. One for 40K and one for 300K, and they're very similar. You do notice that they're different slopes, and part of that's because at room temperature, you'll actually be able to tunnel through both the part 1 and part 2. So you get more capacitor, but it also gives you a thicker capacitor. It's a slightly longer, wider capacitor in terms of the interface thickness. But at 4K, you actually lose that first case. But on the other hand, you have a thinner insulator at 2, and that particular case seems to dominate the behavior. There's probably going to be a lot more characterization of this over the years, but this is the first sense of where this is going. And so that smaller gate SiO2 means you're going to have a different slope. Then we can get into hot electron injection, and this gets to be a lot of fun. Somebody's going, are we really want to let her get going on this topic? This is kind of dangerous. This will be fun. And so what you end up getting is you can look at the band diagrams, and this is talking about what the band diagram would look like at a cryo temperature. And the cool part here is that your depletion regions are almost negligible, which makes all of your efficiencies for tunneling, for all of the hot carrier effects, quite good and relatively ballistic in these structures. And there's a lot to really get into that. In room temperature, you still see the same quasi-ballistic behavior, but you have a few more collisions along the way. So this whole depletion region is just an amazing area to kind of analyze and see what happens. So this high carrier efficiency with almost no depletion region really can give us some interesting results. And in fact, you can take a look at the device at 300K and basically take a look at a current, and we just, again, going to be doing this for moderately above threshold currents, just slightly above the threshold to kind of show sort of similar quantities. Typically easier to get above threshold currents above in the cryo regions, and so this is why we would do that. So we're going to see above threshold measurements, but we can still handle this and model this very carefully. We can also see at 4 degrees Kelvin a very similar case of injection over time. You can argue it's a little bit faster and a little bit more efficient, and that certainly tends to work out, and we can kind of look at the comparison of these curves in both cases. This was, of course, all done with VDD at still 5 volts, which meant the drain voltage was sitting at ground, so 5 volts in both cases for both measurements. So much more could be done in this, and we're looking forward to doing it, but to kind of show that you can actually get sort of the initial curves, you can actually characterize injection current versus channel current, both at 300K and at 4K, and you can kind of see a very similar behavior. Both of these are operating for the above threshold side of the operation, but clearly it demonstrates the hot electron injection physics. And so as a result, we show that we definitely get the floating gate operation, both at 4K and at 300K. And it's really cool because then we get sort of this sort of operation. We definitely had no trouble retention throughout any of the measurements. Not surprising, we never have measurement trouble with this anyways, even at 300K, and we expect as we cool it, it would get better. Transistor operation seems to be exactly as we would expect, and the program in arrays works as you would expect, and there's certainly much more to characterize through that. And this also then allows us to ask questions like maybe potentially FPAs, and there's more to be said in that space of what you could do with a much larger computing structure. And even more, this could have a huge impact and huge implication for areas in quantum computing and related structures.